Hello, my name is Paul Kennedy. I'm the host of a radio program on CBC here in Canada called Ideas. It is a great job, and one of the best parts of the job, as far as I'm concerned, is the annual tour every year with the Massey Lecturer. The Masseys have been on the CBC for more than 50 years, half a century, and some of the lecturers in the past have been truly amazing. Doris Lessing, Martin Luther King, Billy Brandt. I could go on, but it would take up too much time, and we want to get into this conversation with this year's lecturer, Neil Turok. Mr. Turok is a prominent physicist and a cosmologist. He's the director of the Perimeter Institute here in Waterloo, Ontario, and we will be spending approximately the next 45 minutes discussing the Massey Lectures, the 2012 Massey Lectures, with Neil. And this will be the beginning, really, of something we're calling the Massey Experience, which has plenty of opportunity for you to chime in and become part of that experience. Tonight, you can chime in by twittering, by tweeting, by sending comments or questions to us here in Waterloo. And we actually have Greg Dick, who is involved here with the Perimeter Institute. He will be monitoring those tweets as they come in, and we'll be trying to feed that into the live broadcast. It is a lot that we have on our plate tonight. There's a whole universe, quite literally, to explore. I want to begin by thanking Neil and congratulating him for this book, which has just recently come out, which is The Universe Within, From Quantum to Cosmos, which is, in fact, the text, the print version of the Massey Lectures. And the way I want to proceed as the evening goes on now is, what I'm going to do is I'm going to take short quotations that Neil wrote from the book. I'll throw the quotations at him, at you, Neil, and I'll ask you to elaborate on them briefly by way of explaining what you're thinking, what you're hoping to communicate. First one is a quotation that I think could be really something that's descriptive of the whole book, of the whole series of lectures. And the quotation is, "We are analog beings living in a digital world facing a quantum future." Please explain.
Okay. Well, it's a big topic, as you mentioned, but I think my starting point in the book is really the unhappiness which is prevalent in our society, maybe summed up by a comedian, Louis C.K., when he said, everything is amazing right now, but nobody's happy. And he was talking about the internet on aeroplanes, for example. And I think there is a widespread feeling that the deluge of digital information, which is coming at us all, and of course creating many wonderful things, opportunities to communicate and to educate and so on, is also feels rather alien to us as natural living creatures. And so that phrase summarizes the feeling, first of all, that we really, as human beings, appreciate analog things more than digital. We like continuous, smooth, pleasant things like art and music and the natural world. And as a mathematician or mathematical physicist, it's very obvious that something which is continuous contains far more information than something digital. Digital just means zeros and ones, and there's nothing more brutal than a 0 or a 1, and it's the lowest form of information. So when people talk about the digital revolution, it always feels to me they're missing the point. This is, in a sense, bringing us all down to the lowest possible form of information. Of course, the exciting thing is what's ahead of us is quantum computers, quantum information, quantum communication. And I think this message has really not got out there yet, that what is just around the corner are computers and electronic devices that will operate in truly quantum ways. And so there are three levels of information: digital, analog, and quantum. And quantum is really a realm of information above us. It will extend us, it will change us, and in the book I speculate about the next form of life being quantum life, where for us, our digital genes are the code behind us. We're not digital beings, at least I hope not, but we're coded for by digital code, and in the same way I believe that us as analog beings will code for quantum life, the machinery of which will, if you like, be quantum computers.
What's refreshing about that attitude, which is very much part of the lectures, is that it runs counter to something, to quote a previous Massey lecturer, Douglas Copeland, a few years ago. He said it one night after the lecture. I remember him saying, acceleration is accelerating. And I found that scary. But he found it, and I think you find it exciting. I mean, we are entering a brave new world.
We are. We always have been, since the Middle Ages and the Italian Renaissance. The pace of scientific progress has been enormous, and it's speeding up. And I think, again, in today's world, people worry much too much about the present. People don't take a long-term view enough. And so a big theme of the book is that we have these unbelievable capabilities within us. Just look at what we've done so far. Look at where the science is leading us. And how you can be pessimistic about the future, I simply don't understand, because I think the prospects are phenomenal.
I'll give you another quote now, which I think underlies that, and also is, as you say, one of the themes of the lectures, the book, and that is the empowerment that comes from that kind of knowledge, the kind of knowledge you're describing. The quotation, "Science is all about people. They may work in labs and scribble strange formulae, but they're driven by the same natural curiosity we are all born with, to explore and discover our world and what we can do."
Right. So maybe an unusual feature of the book is I try to connect things like love and hope with physics. And through history, there has been this separation. You know, physicists are supposed to be technical people who just get on with it and make things work, but they don't necessarily think about why they are doing it, and they're not necessarily motivated by, you know, some passion. And I think that's a problem both for society and for physicists, that we need to, as I say in the book, we need to connect our hearts with our minds, and realize that understanding the universe is a part of who we are. It's almost a defining characteristic of human beings and human society, that as we understand the universe and realize how to use it, we change our world. And this change is bringing more and more possibilities for us. I mean, obviously the very futuristic ones are space travel and this idea of quantum computers and so on. But it's always amazing to me how people who are outside science or physics more or less are waiting passively for the next gadget or invention to appear, instead of saying, we need to create the conditions in which the brilliant minds of the future are going to make the discoveries which will enable our future to be fantastic. And everybody has a role to play in appreciating how important science is and how important it is to encourage young people to do it.
I think Greg has something from the Twitter sphere.
The Twitter sphere from @DaveRolick. I teach high school physics. What advice would you give a student as they enter an undergrad physics program?
I would say keep your eye on the big picture. Physics can be an off-putting subject, and I know because my daughter has just been doing it in her college, because it's such an old subject and there's such a vast body of knowledge, and it's solid knowledge. This is not really going to change. The laws of mechanics and electromagnetism and so on. There's so much to learn. So it's a mountain of knowledge, and we're at the cutting edge of physics. One is building on that mountain. So it's scary as a young person to think, wow, I'm going to have to study for 5 years before I get to anything really interesting. And I would say the most important thing you have is your enthusiasm. Okay, and without it, you'll get nowhere. With it, you will be able to put up with the pain and suffering you have to go through to learn all this stuff. But it will pay off, because when something clicks and you realize this is actually how the world works, this is what light is, This is how atoms work. This is how our bodies function. And it's all made possible by physics. I think that's one of the most beautiful things beautiful experiences you can have to understand. So I would say it's well worth it, but don't be put off by the kind of mechanical side of it.
Let's move from physics to mathematics, which are related but not the same.
Yes.
Mathematics is our third eye, allowing us to see and understand how things work in realms so remote from our experience they cannot be visualized.
Yes, well, the classic example in the last few months was the discovery of the Higgs boson. This is something anticipated in the early 60s on the basis of mathematical arguments based in turn on very profound principles of how people believed the world worked through relativity and quantum mechanics, and this led them to the Higgs boson. It's simply staggering that we have this ability to understand nature on a scale of 1/billionth the size of an atom, okay? And it works. The Higgs particle was predicted. People built the greatest experiment of all time, the Large Hadron Collider, and bingo, there it was, exactly where it was expected. And on the other end of the spectrum, we have understood the whole universe. This is us, ordinary, monkeys, okay, managed to figure out how the universe works on a scale 10 trillion times the size of the solar system. And so again, there were theories. There was Einstein's theory of gravity. There was the theory of radiation and heat. And these were applied on the largest scales imaginable. And they work. They work spectacularly well. So again, to me, this is something we should take strength from and courage from. We are, one of the phrases which I quote in the book is a lovely quote from Julian Huxley, who's an evolutionary biologist. And he says, we are the means for the universe to become conscious of itself. And so I love this because it implies we are part of nature. We have these amazing capacities. They come from the universe. The universe teaches us things, and in the process, we advance our society, and we pave the way for the future.
I have to say that reading the book and in hearing you talk, although you're a physicist, what the words that came into my mind quite frequently are poetic. I mean, what you just said could be written in 4 short lines: to see the world in a grain of sand and heaven in a wildflower, hold infinity in the palm of your hand,
exactly.
And eternity in an hour. Blake was a physicist?
Exactly, he was.
Who knew?
That is why we do physics.
Okay. More Twitter.
Yes, we do. From @Georgina Devaris, loving the Massey kickoff. Question: science is all about people, so what changes would you make to education today? #Massey's.
That's a wonderful question, and I think part of the pleasure of doing the book was reading about the lives of people who got into science. I mean, tracing all the way back to the ancient Greeks. But I'll pick one example, which was Maxwell. And Maxwell had a very lucky childhood. Well, in some respects. I mean, his mother died when he was 8, I think. So he was raised by his father. But he was on this, minor aristocratic family in Scotland. So they had a little estate, and he went running around collecting insects and playing with, streams, and they had bell wires in the house that he played with. And he was just this incredibly playful child, and being in that kind of environment, he was encouraged. And the consequence was this unbelievably creative scientist who studied everything from the rings of Saturn to the color, made the first color photograph, and so many things he just played with. And then he discovered what light was. And so when I look at today's education system, I always ask, how would it treat Maxwell? He was an oddball. I mean, many of these brilliant young kids are oddballs. He was not somebody to study, systematically and learn for exams. When he took the exams at Cambridge, they said he doesn't study properly at all. He's just messing around with, doesn't do anything until the day before the exam. Just goes in and sees what he can do. And he didn't come top in Cambridge. But so I think what I would love to see more of in schools is the encouragement of play, of independent thinking, of creativity, rather than a rather rigid curriculum that you force students through and make them memorize stuff. And unfortunately, I think the internet has not really helped the tendencies which were there in the system already. There's just more of the same. And I would love to see kids encouraged to be more human and natural and curious and so on.
The next quotation I selected is very epigrammatic, and it's also something I think is really central to the theme that you're pushing all the way through the lectures. When we look up at the sky, we're actually seeing inside ourselves.
Right.
That's Blake.
Good, I'm glad to hear it. Yes, I think, again, we have this capability, for reasons we do not understand, to comprehend and make use of the whole universe. It is a miracle. One way I think about it is it's a kind of, physics is really a message from the future. It's as if we stumbled upon, and maths, stumbled upon 1 + 1 = 2. I mean, this is a very, very profound truth. And we still don't know its significance. We don't know why math works to describe the world. We don't really understand the relationship between ideas and reality. What we know is that our ideas, some of our ideas, work to incredible precision. And so this message from the future, which is how I see physics, is telling us something about who we are. And when we look out at the universe, we're receiving these messages, which are telling us what happened at the Big Bang, so where we came from. And they're telling us how the world works. I mean, we've just discovered dark energy. We've discovered that empty space is full of energy. We've discovered dark matter. These are profoundly important discoveries which will lay the ground for future technology. And so the universe is teaching us and telling us who we are and where we are going. So indeed, I think it's the same thing I said before, that we are part of the universe. And to understand that and to see it as a guide to where we came from and where we're going is, for me, very important.
Greg, what are people saying in the universe of Twitter?
I've had this question more than once. It's simple. What banged?
So that question came to me from my primary school teacher, who, when I tried to explain my technical work, she said, I don't really want to know about string theory and 11 dimensions, and nor do I want to know about all the latest observations and the telescopes and apparatuses you're using. I just want to know what actually happened. What happened? Where did all this come from? And so I was interested in that anyway, but her question really motivated me to focus on the most fundamental aspects of that question. Can we somehow glean from the information we have and the theories we have the answer to that very simple question? The amazing thing is that we're quite close. We have I don't want to tell you about all the instruments and apparatus, but we are close. And in fact, so discoveries like the Higgs boson are one new clue. They're aspects of the data, the Higgs data, the actual mass of the Higgs boson, that are telling us about physics at an energy so high that it governed the Big Bang. And so this hasn't been talked about much, but there are clues, very important clues emerging about what really happened at the Big Bang. And again, this is something I'm very optimistic about, that at some point we will settle the question, was the Big Bang the beginning of the universe, the beginning of time, or was it instead a violent event in a previously existing universe? The amazing thing is that we're able to tackle these problems in a totally logical, experimentally relevant way now. And these are problems which the Greek philosophers and everyone since have wondered about.
So we are on the edge of a great new understanding of everything.
Yes, I'm sure. I'm not sure if my confidence means anything, but
it means more than mine would, actually.
For what it's worth, I mean, all my experience in my scientific career is that when you are working on something that seems impossible, but you feel you're making progress, then 10 years down the line, it will be in the realm of the testable. And I've had that experience many times. We did calculations in the mid-90s, which the experimentalists told us were never going to be checked, just way too small effects that couldn't be seen. In fact, one of them was a way to detect the dark energy. And a few months ago, that method we proposed has been used, and it's been measured at 99.996% confidence that the dark energy is there with that test. So my rule of thumb is never believe people who say this is beyond the limits of experiment or technology. If your ideas are right, and if they're clear and precise, and in principle possible, it will probably happen.
Actually, I want to ask a supplementary really to the Twitter question that came in. It was about a teacher. You came up with a response saying it was a teacher. You're very interested in education, and it's as central to the work that you're doing as physics is. It's something you care about a great deal. In your own life, she was plainly a teacher who intervened in a very successful and important fashion. Yes. How many good teachers have you had like that?
She was the best. Yeah. And she taught me, I think, when I was 8 or 9 years old.
Still playful.
Yes. And so what was very special about her was she told me to go outside, to make a plan of the school, to do experiments with water and check Archimedes' principle, and things like that. She learned this from her training in Scotland. Scotland, and this goes all the way back to the 1700s and the Scottish Enlightenment, Scotland developed this tradition of outstanding math and science education based on the fundamentals, on a questioning of everything, including the basics. And that was the system she came out of, and produced some amazing teachers.
And the Edinburgh Enlightenment you refer to is also a place where David Hume would have dinner with Adam Smith and Walter Scott.
Exactly.
So that there were no boundaries between disciplines. A philosopher, an economist, and an author, a novelist could be in the same room at the same time discussing things that they could discuss together.
Exactly. So I draw a parallel between Scotland in the 1700s and Canada in the 21st century, because I do feel that the conditions in Canada, there are lots of parallels. Scotland was nearby England, which was busy engaged in its colonial wars, and they left Scotland alone for a little while.
Very briefly.
Canada is, a neighbor of the US, which is certainly our modern Rome. And I see Canada with its education system and its society, its very tolerant and diverse society, as a model for the world. And I think if Canada grasps this idea that that Canada can foster an enlightenment on the scale of the Scottish Enlightenment, this will be a wonderful thing.
The next quotation takes us into a similar sort of realm, that is comparing across time intellectual societies and engagements. Throughout history, from Anaximander to Pythagoras to Galileo and Newton, the universe has been an endless source of wonder, inspiring us to rise above our current circumstances and see what lies beyond.
Right. Yes, this again was a very fun part of writing the book, was learning about this history and seeing the common strand that runs through it. So if you take Anaximander and Pythagoras, you know, one was more experimental / observationally driven. Anaximander figured out how to make maps, which was our the first way of sort of quantifying space. So he made the first map, and the first map of the world. And then you have Pythagoras, who was the mathematician, more abstract. And similarly, you have Galileo, who founded the idea of scientific experiments and tests, and Newton, who used Galileo's intuitions to make mathematical models which work to incredible precision. And similarly, you see Faraday, who was the experimentalist, and Maxwell, who was the mathematically minded person. So, so this combination of the side of talents has sort of driven the progress of physics in history. And what I particularly like in looking back to let's say, to ancient Greece, is it just blows your mind how they were able to disregard the superstitions and the orthodoxies of the time and just look at the world with fresh eyes and figure out how it works. And at the same time, they were figuring out how society should work, and they invented democracy and so on. And they had a totally different view of the universe. You know, one of the interesting quotes, I guess the most famous quotes of Einstein, is the most incomprehensible thing about the universe is that it's comprehensible. And if Einstein said that, you know, the rest of us should be fairly puzzled. What chance have the rest of us got? But I would say that statement is a reflection of our society and the divergence of science from the rest of humanity. Because in ancient Greece, they didn't see it that way at all. They saw ourselves as part of the universe. And of course we can understand the universe. We are the universe. And the universe, you know, they invented the word cosmos. And it was supposed to be the ultimate in beauty and truth, and it's the divine thing. And we are part of it. And they believed we would understand the universe. On the basis of very little evidence, as far as I can see. You know, Pythagoras basically had music. He saw music, and he realized music is mathematical. And he thought, oh wow, if music is mathematical, maybe the planets are mathematical. Maybe the whole world is mathematical. And he was dead right. Okay. Likewise, the Greeks invented the word theory. And theory in Greek means, I see the divine. And so to make a theory is to gain insight into the universe. So personally, I feel that this view of ourselves as a part of the universe is something we need to get back to. And I think things like the digital revolution, which are kind of dazzling us with this inhuman form of massive information, I think we should take heart that the quantum revolution is coming. And this will take us back to how nature actually works. And that's the root of progress.
Another theme that I want to follow up on there is that not only is it cooperative and is it inspired by a sense of wonder, a sort of radical doubting or wondering what things are about, not accepting anything, but it's also built on a cumulative kind of basis. I mean, nobody is alone. Everybody is working with something that was given to them, was sort
Right.
of handed down
Right.
by predecessors or colleagues at the same
That's
time.
right.
I mean, this is not individualism run
Right.
rampant. This is, in fact, some more communal, corporate, organic structure almost.
Yes, it is. And I think, again, tracing the history is really interesting, because this idea that somebody, that a young thinker sort of serves an apprenticeship with a more experienced thinker, or it goes right back to ancient Greece. And Thales taught Anaximander. And as far as we know, Anaximander taught Pythagoras. And these were very different people with very different ideas and skills and so on. But they had this culture of conveying knowledge from one generation to the next. And this is absolutely characteristic of physics. This is the way physics works at our institute, is we have a mix of very senior people who are experienced and wise and know all the standard stuff backwards. And then we have very young people who know very little, but are very motivated, and it's going to be the young people who have the new ideas. And so I think physics, in the way it operates, in this sharing of the journey and realizing that the young people are the future, but the more senior people are there to pave the way for them, is again a good model for society.
And it's something, as you see, you're creating it here.
Yes.
There's like a critical mass that happens
Yes.
when you sit in a cafeteria, when you're surrounded by very disparate minds,
Right.
but minds who can think outside their own minds and communicate and have some sort of a conversation with
Right.
people who are thinking different things.
Right. I mean, I think I would claim, and make a very strong claim, that theoretical physics is the first science, the most basic science. And of course, it should lead the way in the way science is organized. It always has led the way. I mean, physics created the internet. And theoretical physics is the most abstract, intangible science you can imagine. But what we're trying to do here is to, carefully and strategically create a center which is like the center, like what happened in ancient Greece when the scholars came together and somehow were able to reconceptualize the universe. That's our inspiration for what happens here.
I was a graduate student of Marshall McLuhan's, who the most interesting thing I ever heard him say was one day when he was very upset with the university. And he said, "The problem, Paul, is that this is not a university, this is a multiversity." And that is that people can't talk to one another.
Right.
That mathematicians can't even talk to physicists,
Right.
let alone talk to people who are working in the English literature department,
Right.
or in philosophy or in political science.
That's right.
And that breaking down the walls was something he felt was very, very important. And he was very depressed when he was dealing in situations where he didn't think anyone wanted to talk to him.
That's very interesting, because one of our favorite slogans here is that there are no groups. So we just refuse to recognize groups of researchers who are focusing on some area. Of course, people may decide to clump together and address some problem, but we will not recognize them administratively as a separate entity with the right to money or funding or whatever. Because, as you say, the most fruitful science is almost invariably done when people from different backgrounds and with different expertise interact and create something new. So it's one of the great problems of the university, the fragmentation of knowledge. It's just too many people and too many disciplines, and not enough focus on, let's say, the really important problems which are beyond any of our existing disciplines. So for sure, in our institute, I mean, we're extremely lucky that we have the freedom to design the environment and the way the research is done to deliberately encourage collisions between people from with different backgrounds. universities in general don't have the flexibility to do that. It's more difficult. To some extent, they've become fossilized in a model which was relevant to the Middle Ages.
I'm sure there are many academics who look with envy on what you do here, though.
Yeah.
That they would
I do
like to be
too.
here.
I was one of them.
Greg, another question or a comment from Twitter.
Both. This harkening back to when you were talking to Pythagoras. So @PaulMath says, do you think math is invented or discovered? By the way, we need a keynote speaker for our Provincial Math Educator Conference in 2014.
I think math is a miracle. I don't think it was invented. I think it is there. It's so you see, it's telling us something very deep about the world, the fact that math exists. And I can't say more than that. I don't really have a clear answer. And if you ask physicists, what is math? I mean, it's just a tool we use. And what are physicists doing? We're driven by this idea that we can understand the universe. Okay, that's certainly what drives us. It's an amazing thing that we can do that. But aside from that, we're essentially following our noses. Okay, so Maxwell made these spectacular discoveries, and then Einstein on top of that, and Dirac, and we're just the next generation. We're doing our little bit, and if we can add even a tiny amount to this amazing body of knowledge, we consider that a big success. So I think I really do view it, math and physics, as a miracle. And somehow pulling on the thread will take us where we need to go. And there's just no question that is extremely important for the future of the world.
We have a question from the audience.
My question is, how do you feel that a deeper understanding of the cosmos helps us influence our work towards a more sustainable life on Earth?
Yeah, it's a good question, and it's one I ask myself about a lot. You might say working on cosmology is a luxury. The world may come to an end in 50 years or 100 years when we run out of fuel and destroy the environment and are plagued by disease or whatever. But again, look to the past. I mean, where did this modern world come from? Where did plumbing come from? Electricity and roads and supermarkets and all the stuff we absolutely take for granted. And the answer is that it came from the discoveries made by people like Isaac Newton, who discovered the laws of motion. He couldn't do engineering without those laws of forces and movement. And where did Newton learn those laws? Well, he learned them from the universe. He learned them by understanding how the solar system works and fitting the observations people have made. And this is true of all the progress. Where did lasers come from? It didn't come from worrying about, the problems of the streets or it came about worrying about the vacuum and what is light, what is nature. And so why should we lose confidence in our best means of making progress happen, when it is happening faster than ever? I think now is absolutely not the time to say, enough physics, okay, let's solve some real problems. Because the real problems have to be solved, okay, but the way I see it, those real problems need to be solved by very practical planning, rational thinking. These are all problems which can be solved if people are sensible. Okay, how to make people sensible is another question, which physics is not going to solve that one. But essentially, those are practical problems. What physics will do is open the door to the future, and I don't think we should be closing it right now.
think we have time for one more quotation from The Universe Within. And this one, again, in some ways, sums it all up. It's all in this one little grain of sand. The universe is not like a machine or a digital computer. It operates on quantum laws whose full meaning and implications we are still discovering. According to these laws, we are not irrelevant bystanders.
Well, this is one of the most wonderful things about quantum theory. We don't live in a clockwork universe. And I think many people outside of physics believe that physics is all about understanding the machine, that the universe is a machine with laws and what happens is inevitable. Now that model of physics was disproven in the early 20th century. We know physics doesn't work, the world doesn't work as a machine. It's a quantum world, and that's a very abstract statement, and we're struggling to understand what it really means. We have been ever since the 1920s. But we know that concepts like the square root of -1, which is the I, in fact, that's the real third I, the I, which I talk about in the book, not the iPhone or the iPad either, the real I is the square root of -1, and that's at the heart of quantum theory, and somehow that is fundamental to reality. And we're struggling to figure out how. But what we do know from quantum theory is that what you get in the result of an experiment depends on what you decide to look at. We're not just bystanders. When we make an observation, the results, we have the freedom to choose what to measure, and what we get depends on what we measure. And people, this is at the forefront of quantum information theory right now, to understand exactly what this means. And some people are worrying about, does it mean there's free will in quantum theory? And could we make a theory of free will? And so these are frontier topics which haven't been resolved at all. But I think everything, quantum theory clearly tells us that we are an integral part of determining the evolution of the universe. And we're not, as I say, we're not just bystanders.
I think we have time for one more question from Twitter.
Okay. And I have two if you give me time. Joshua Butcher says, Neil, what problem of today do you see as a distraction, keeping us from what you say is what lies beyond?
The problem of today as a distraction, well, I mean, there are many problems today. I wouldn't call them all I think that, these problems need to be dealt with, whether it's hunger or water, or we have to deal with these problems. But I think the first part of dealing with problems is having the confidence that you can deal with them and that there is a future worth making. I mean, people need to be motivated to believe in a future which is worth living for. And I think without thinking of what lies beyond our immediate problems, we're in danger of basically sitting glued to our computer screens and responding to emails endlessly and getting more and more drained and pessimistic as the world sort of spirals into ever greater financial crises and political battles and all kinds of nonsense. Okay. And so I think it's incredibly important to see beyond all that stuff, and for people to realize there's a brilliant future waiting for us. We need to drop our petty differences and selfish behavior. I mean, one of the points I make in the book is that so much of the problems of society are driven by selfish behavior, whether it's the financial crisis or pollution or environmental destruction. It's simply selfish behavior, and I think if people can see beyond to a wonderful world that is ahead of us, which I'm sure we will reach anyway, that will hopefully help them to adopt better values. Again, to ancient Greece, where did values come from? It came from the same philosophers who were worrying about how the universe worked. They also worried about what is the optimal way for human beings to interact. What are the principles, like the principle of reciprocity, that we shouldn't treat anyone else in ways which we wouldn't like to be treated ourselves. And so it was all one, and I hope it will be all one again.
Thanks, Neil. We've come to the end of our allotted time here, but I want to say that this is really just the beginning of what we're calling the Massey experience. And everyone should remember that in the next several weeks, as the lecture tour crosses the country with Neil, going first from St. John's in Montreal over to Vancouver and Calgary, there will be a website. There is a website up that just went up today, in fact, which is called cbc.ca/Masseys. It's the Massey experience. You can find out information there about how to get 2 tickets for those lectures in those various cities. There's a link as well that will connect you with the House of Anansi, which publishes the book, and you can order a copy of the book as well. And it gets better still, because there is a contest being sponsored, in fact, here by the Perimeter Institute, with a prize. I talked to a couple people about this yesterday, and they want to be part of this contest, because the prize is to get to meet Neil, and you'll get 2 tickets that will take you to Geneva, Switzerland, where you'll be able to see that amazing device there, which underlines a lot of your own work and much of the experimental stuff that is now being done in physics. So all of that is there on the Massey experience, cbc.ca/Masseys. That's about it for now. I think this has been a great way to begin the Massey experience. It's fascinating to chat with you. Maybe I think the best thing is that everything you say is full of hope. And this is a time when we don't get enough of that kind of message, I think. This is hope grounded in science, which for a humanist like me makes my heart tick a little faster, I guess. Anyway, thanks to you, Neil. Thanks to the folks here in the audience at the Perimeter Institute. Thanks for everyone watching out there on the web right now. And welcome to the Massey world. Congratulations on being the 2012 CBC Massey Lecturer.
Thank you.
Thank you, and thank you.